Okay, let's start the exercises then. Yeah, so I'm not writing the first, the 24 bijections, sorry, injections from this set to this set. I'm just going to show you either 24 and that, you choose three out of four. You just spend three of these. So you choose three out of four and then you send them to all six permutations of them, right? Yeah, so that's how you get 24 of them. I mean, I am not writing them all. So yeah, okay. And for a similar reason, we get 10 choose 8. Um, oh, times 8 factorial injective maps. Yeah, yeah, that's how many you get, and it's 45 times whatever this number is. It's certainly more than 720 times 7. So more than 4,000. Yeah, this number is more than 4,000. So yes, no point in proving. Okay, so we are assuming B is a subset of A. We have to show that if B is not finite, so that's how I'm going to write it. So it worked out. Implies A is not finite, right? So I'm just follow it as a notation, right? It's the negative of this, right? So this is the contrapositive by the notation. Now this is true by this by the corollary. So it's the contrapositive, and therefore this is equivalent to this. And since this is true, this is true. So we're done. Yeah, okay. So yeah, so we have x omega and a proper subset of x omega, right? Okay. So surely the set of all functions that start with 0 is a proper subset of x omega, x to the power omega. So I'm just going to write it as x bar x of 1 is equal to 0, right? So clearly this is a proper subset of omega as we have 1 comma all ones that's not a member of this, right? So it's a proper subset. And yeah, so the bijection is simply x of I plus 1 is equal to x of y of I, right? So this is a bijection from omega, x to the omega to x to the omega, y to x, right? So, and x of 1 is equal to 0. Yeah. So this is a bijection because so all functions are covered here essentially. So take any function, you shift it. There exists a function that is, such that g of y is equal to x, right? So that's fine, and it's 1 1 because if they're equal, then the whole function is equal, right? The whole of y is equal to the other y prime. The same thing in we covered in Cartesian products, which I didn't do that much in detail, but yeah. So it's a bijective function, and this shows that x to the power omega is not finite. Yeah. Later we'll show that it's uncountable, but that's a whole other story. Okay. Yeah. Yeah. So A is a finite set, I believe. Yeah, finite and simply ordered set. notation. Just take it as notation. Yeah. Now, if A has cardinality 1 or 0, if A has cardinality 0, then it stops being a simply ordered set, or maybe it is, I'm not sure. It's trivial in either case, right? There is no largest element in the cardinality 0 case, and there is only one largest element in the 1 case, which is the only element. So we're fine. So now we have to show that it's true for all n by induction. So for finite sets, that's the method, right? So assume it's true for all sets of cardinality less than n. Um, yeah, all sets of cardinality less than equal to n, and just using cardinality. It's just notation, just yeah. And now we have to show for that this applies for sets of cardinality uh, n plus 1. Note that cardinalities are unique, so we can write this. Okay, so fix a member a naught in A, right? Since a naught is non-empty, uh, because otherwise if it's empty, then it doesn't have a cardinality n plus 1, so it's definitely non-empty. Now, A minus A naught has cardinality n, so it's a bijective correspondence with slice 1 comma n. So is it 1 comma n minus 1? Yeah, it has the bijective correspondence with set. Uh, yeah, yeah, by the theorem, right? And by inductive hypothesis, there is the largest member in this set, and let's call it A, A1. So A1 is the largest member in this set. Now, since A is a simply ordered set, either A1 is greater than A0 or A1 is less than A0. A1 equals to A0 causes a contradiction because A1 is supposed to not be in the set, this set. So it can only be these two. Now, in this case, A naught is the largest member, and in this case, A1 is the largest member. Why? So it's greater than all members here, and it's greater than A naught. So it's greater than all members of K. And in this case, yeah, A naught is greater than A1 and therefore greater than all members by transitivity. So we have a largest member um, for all finite sets, right? Because it's uh, bijective with in a bijective correspondence with a slice of integers or section, yeah, the section. So yeah, this may be shorter than the theory portion. I can make it. So yeah, let's assume by inductive hypothesis again. So the set one, which is the biject in biject, if it has a cardinality one, then one is a section of positive integers and the order type is trivially equal. And same thing with cardinality zero, right? Now we show it for n plus one, given it's true for all 1 to n, right? So simply choose the largest. So we have A. Now choose the largest member A naught, right? Now A minus A naught is in a bijective correspondence with this set by the theorem. And by inductive hypothesis, they have the same order type, right? So for to have the same order type, they have to be a bijection and order preserving. So since they're already a bijection, there kind of has to be an order preservation too by the inductive hypothesis. And define f, f prime. So we define f is equal to f prime for I less than equal to n, and f of I is equal to f, so f of n plus 1, hang on, f of n plus 1 is equal to A naught, right? And since n plus 1 is the largest member of this set, A naught is the largest member of this new set, so it's fine. And the other part is in the same order type, right? So because of that, for all members of A naught, the F is preserving the order, preserving, preserving the order. All right. Yeah. Yes. If uh, not necessarily A cross B being finite does not imply that A and B are finite. And the simple counterexample is if B is an empty set. So since Z plus is not finite, that's proven. Z plus cross phi is equal to phi, which is finite, but Z plus is not finite. So yeah. But if both of them are not empty, then since they're not empty, we have a bijective correspondence of A cross B to B, which is this is a finite set as it's a subset of a finite set, and this is a finite set because it's in bijective correspondence with a finite set. And the same thing for A. So because of that, A and B then do become finite, but not if only if they're not empty. So yeah. Uh-huh. Okay. Yeah. So power set of A to x to the power n, right? And x is equal to this, and set theorists will call this the number two. Yeah, it's a thing. And addition is defined in a way. Yeah, it's something. Yeah. Anyways, so yeah. So let A be a subset of A, right? And okay, I shouldn't use A. What should I use here? Okay, I'm going to write alpha then. Yeah, alpha. So yeah, so first I'll invoke the bijective correspondence of so since A is a finite set, it has a cardinality that's an integer, so I'll take n, right? So we have this bijective correspondence, right? And if f of I belongs to alpha, then so I'll call it G, then G of I. So this is what a function from ultimately this is the set of all functions from 1 to n to x, right? So yeah, this is going to be so this g of I is actually x of I. I should correct that. Or more like, xi is equal to something. Yeah, it can be defined. Xi is equal to 1 and it's equal to 0 otherwise. So it will either belong to alpha or not belong to alpha, right? So yeah. Now let's say we have any arbitrary function from 1 to n to x, right? Hang on, just checking the question. Oh, okay, that simplifies a lot. A is not a finite set. A is the set 1 comma n itself. That simplifies things a lot. Okay. Oh, yeah, just instead of f of I, you just need to write I instead, right? Yeah. Let's change this. Yeah. 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 I belongs to alpha. Yeah. And alpha is a subset of, yeah, that simplifies a lot of things. Okay, so for any function from 1 to n to x, essentially if it's zero, include it in the set, and if it's not, then don't. So yeah, we'll get a subset that way. So we can construct a subset from a function, so it's surjective, and since we're having the function has to be defined on all subsets, and it's injective because if the two functions are equal, then the sets are equal, right? Since they'll have the exact same members, since they're both subsets of one comma n. So yeah, the characteristic functions represent the power set. Essentially, every subset is represented by a characteristic function. And this extends to x to the power omega as well, and you'll find out. Show that if A is finite, then power set of A is finite. Okay, so yeah, x is finite. Is x finite? Yeah, x is finite as it's 0, comma 1, which is by definition finite, since there's a bijection 1, comma 2, right? There's a bijection, so it's finite. Trivial. That's pretty trivial. Okay. Now, x to the power n is also finite as a finite Cartesian product is finite, right? Now, A is finite, therefore it has cardinality n, right? Whatever, you get it, you get it. Right side if you want. Yeah. So, given that it's finite, power set of A has a bijective correspondence with x to the power n, and x to the power n is finite, right? So, power set of A is finite. And we're done. Okay, last question is just an application of this one. So, observe that every function is a subset of A cross B, right? So the set of all functions is a subset of power set of A cross B, right? Correct? And A cross B is finite, right? It's given to us. So that's because A and B are finite, I believe. Yeah. So A and B are finite. Yeah. Which implies finite. And since we have a subset of a finite set, it's finite. So yeah, we're done.